Thank you very much. Yeah, I want to thank the workshop organizer for providing me the opportunity to present this talk. And the goal is to present how to use optimal transport to measure the distance between measure, and in particular for this case, how to find the closest, so given a measure mu, how to find the closest mixture of Gaussian that minimize two distances, the Wasserstein and the total variation. So it's based on two papers, and that one is already published, and the other one is on archive. And what is the statement of the problem? So we are given a measure mu on RD, okay? And the knowledge about this measure is through its moments. So we are given moments of the measure mu, okay? Multi-index alpha. For every multi-index alpha, we get the mu alpha, which is the alpha moment of mu. And then we denote the usual classical notation by m sigma, the Gaussian measure on RD, with mean m and covariance matrix sigma positive definite. And the classical definition of the density of a Gaussian, or everybody knows that, right? So this m sigma will be the parameter of the Gaussian. And the idea is that we are going to work with a space, given a priori space of parameters. So S will be a space of possible parameters for the mixture of Gaussian we are going to look for. So for example, the mean would be, an example of set S would be that the mean is between two bounds, and the diagonal of the covariance would be bounded below and above, right? So it would be an example of such a set S. And when you take a Gaussian mixture nu phi, okay, so it's defined through a mixing measure. So phi will be a mixing measure that will be a probability measure on the space of parameter m and sigma. And the density of the Gaussian measure nu of phi, so we are going to define a measure nu on the whole space, and its value on the Borel set B is just the integration over on B of the Gaussian, and then through the parameter m sigma through the mixing measure of phi. So nu phi is called the Gaussian mixture, and phi is called the mixing measure on the parameters. Okay?
So here you're considering all mixtures, not necessarily a finite.
Yeah, exactly. So it's good to remark that the specific one specific feature of this approach is that we don't do an a priori discretization of the space of parameters. So we are given instead of a probability measure of phi on the space of parameters, and the goal is to find which is the support of phi. Okay, so given, so statement of the problem is quite simple. So given mu in blue, okay, so mu is given through its moments, find the closest Gaussian mixture nu phi, okay? So we look for a Gaussian measure, a Gaussian mixture, so nu phi here, which is what? It minimizes the distance between mu and nu phi about all possible Gaussian mixture nu phi when phi the support of the probability mixing measure phi is supported on S. Okay, so is it clear? Okay, so the goal is to compute this argmin of this distance, and then for the distance that we will consider, there will be two of them. The first one will be the Wasserstein distance, the square of the Wasserstein distance 2, and the other one will be the total variation. Okay. So as a parenthesis, there was some people who were looking at the converse problem quite some time ago. And in the converse problem, it's just a parenthesis, a detour. I just learned that recently. It's by Guillaume Carlier. And I was looking at the converse problem, namely that now the data that you are given in blue is a finite mixture of Gaussian. So you are given certain Gaussian mi with parameter mi and sigma I, m of them. And you are given the measure nu, which is this convex combination of Gaussian. And the goal in this paper was to find the argmin, a sort of barycenter, to find the measure mu star, where mu belongs to this space here. So X is a space of functions which are grows at infinity is bounded, okay? And we're looking at in the dual of this space with intersect with the space of probability measure. So we are going to look for measure mu, a probability measure mu, that minimize this. It's called barycenter. And it's a nice formulation where you can find that you have an explicit solution to this problem. It turns out that the argmean is a Gaussian measure, where the parameter m, the mean is just given by the sigma of lambda I mi, okay? And the sigma star is just this expression, where this appears in the Wasserstein distance between two Gaussian measures. This is a classical result, right? If you look at an optimal transport, when you have a Gaussian measure with mass mean m, and mi, and look at the Wasserstein distance, then the optimal transport is given by this. So in this characterization of the barycenter, the paper by Agé and Carlier were given an explicit solution to this problem, which is a bit surprising that
why do you restrict to X dual in the problem? What do you want to avoid?
Sorry, the X prime? Yeah. Why? Because you have some assumption on the type of function that you should consider. So you define the dual of this space to give a precise meaning to this problem. And then if you don't have this, probably there are other exotic solutions. And this allows you to provide an explicit solution in complete form, explicit form, okay? So that was the converse problem. So it was a paper in 2011 by Carlier and Agé. And back to our problem. So in our problem, we look at the converse problem of this converse problem. And what is the key result that allows you to do some work, I mean, to do practical computation, is that it's a very nice property of Gaussian measure, not only Gaussian measure, actually, and which is the following, which is well known, actually, that if you look at a mixing measure phi, okay, so you mix several Gaussian measures through the probability measure phi, okay, so you have seen that the density of this new phi is given by this, so you take the density of the Gaussian and you integrate with respect to the parameter, okay. Then what is nice is that if you look at the moment of the Gaussian mixture, you take a particular moment alpha, x alpha d phi, this moment is a polynomial in the parameter m sigma. So if you take a Gaussian measure and you take the moment alpha of the Gaussian measure, it's a polynomial of m and sigma. So when you take the Gaussian mixture, the moment x alpha of the Gaussian mixture is just this polynomial alpha of the parameter integrated with respect to the mixing measure. Okay, and this is a nice property of the moment property of the Gaussian mixture. And of course, this polynomial is explicit. For each alpha, you have an explicit polynomial, which is easy to compute, in terms of the parameter m and sigma. Okay, so if you give an arbitrary multi-index alpha, you can provide an explicit form for this polynomial p alpha of the parameter m sigma. And then the moment of this Gaussian mixture is just this integration of this polynomial through the mixing measure phi. Okay? All right. For example, in dimension 1, it's classical. If you look at the moment, the first moment is just equal to the mean. The second moment is m2 plus sigma 2. The p3, m3 plus 3, m sigma squared, and so on. It's a homogeneous polynomial in m and sigma of degree alpha. Okay? So as a result, and which is really a crucial ingredient in the sequel, is that when you look at the moment of the Gaussian mixture, as we said, it's a generalized moment of the mixing measure. Okay? So that is all moments of the Gaussian mixture translate to generalized moment p alpha d phi of the mixing measure. Okay? And this is this key feature that will be exploited for computing the Wasserstein distance, or the total variation distance, mu minus phi, nu phi, between mu and the Gaussian mixture nu phi. And in fact, this key feature is not proper to Gaussian measure. It's true also for the family of exponential on the positive orthant, or the Poisson distribution, and so on. So not all parametric family are not like that, but many of them, I mean several of them, have this nice feature. So what is the W2 Wasserstein distance in this case? So we denote by Px the space of probability measures on the space X, right? So everybody knows very well this definition, that the W2 distance between mu and nu phi will be the nth over the sort of joint distribution lambda, okay, on x and y. So you minimize, for example, x minus y squared, okay, under the constraint that the marginal with respect to x of lambda is just the mu, and the marginal with respect to y of the joint distribution is nu phi precisely, okay? So this is classical, okay? So now if we go to our problem, that suppose that S is the support of the parameter where you are allowed to do a mixture, all right? So this is given. And then the optimal transfer formulation of this problem is just want to compute tau, which is what? Which is the infimum over the joint distribution lambda and now the mixing measure phi, okay, of this distance, right, which is equal to this nth of lambda phi of x minus y squared d lambda, where the first marginal is equal to mu, the blue, everything in blue is given, but now the second marginal is a bit specific in the sense that it's not given as in a Wasserstein distance classical case. Sorry, I did. Sorry, I made a mistake. Yeah, sorry. Yeah, so the second marginal, you see, now it's an equation between the second marginal of the distribution lambda y, which should be equal to nu phi, but nu phi is also not known. So it's an element of the problem that you have to minimize, okay? So this is the problem that we want to solve. And when is this optimization problem well defined? First question. And the answer is quite simple on a very simple sufficient condition. So we assume from the beginning that S is compact. So this is the space of parameters where you are allowed to do the mixing of parameters. And we assume that mu satisfies the multivariate Karleman condition, which is the growth over the moments, so limitation of the growth. So, and what is nice about this multivariate Karleman condition is that it's a condition only on the marginals. It's a generalization of the Karleman. Karleman condition was given for univariate measure, and it's Nussbaum that generalized this Karleman condition to multivariate case. So it says the following: for each index I, okay, so you look at marginal on the variable xi. So the growth of the moment, the square, the 2g of the moments, okay, the growth is limited. So you have a sort of a limit on the way the even moment grows. Okay, so this series should diverge. Okay. So under the simple condition that S is compact and this the marginal of mu for each I satisfies this Karleman condition, then there exists an optimal solution to this problem that we are just describing on the previous slide. Okay. Of course, the solution is not necessarily unique, but there is an optimal solution. So it's a well-posed problem in the sense that it has an optimal solution. And just to have more insight on what is this Karleman condition, a very simple sufficient condition, which is classical in probability, appears in some book already. The sufficient condition, for example, on mu, is that when you integrate an exponential of the absolute value of xi, then this would be bounded. So this exponential of xi is integrable with respect to mu for each index I. So it's a simple, you don't have to check if this infinite series diverges. You just have to have a measure mu such that this is true. Okay. And crucial in the proof is not very complicated. Just that, you have two crucial ingredients. First, this Karleman condition, which is quite simple to state, but has a very nice property in terms of compactness of the pseudo moment. I don't go into detail so much here. And also we use the fact that the marginal of a Gaussian measure is also a Gaussian measure with this parameter. And then by just this argument and the fact that mu satisfies Karleman condition, it's very easy to prove that the Gaussian mixture nu phi also satisfies Karleman condition. Okay. So then we can formulate another formulation of this infinite dimensional problem that we are describing below. That now we can this formulation. Now you replace the condition that the marginal of the joint distribution lambda on x, the marginal with x should be equal to mu, then you can replace, this is equivalent to saying that all the moments of the marginal of lambda x should be equal to mu alpha. So you have an equivalence between saying that the two measures are equal or saying that their moments are equal. And this is a nice property of Kalman condition. When a measure mu satisfies Kalman condition, it is called moment determinate, meaning that if you know all the moments of this measure, you know the measure. So there cannot be another measure mu with the same moments. Okay? This is a nice property of the Kalman condition. And then, so you can replace the equality of lambda x and mu by the equality of moments. Same thing for the Gaussian mixture. You say that all moments of this lambda y and nu phi are the same. And then this problem now has countably many linear equations, linear constraints, but it is completely equivalent to the previous problem. And what is nice to go from the previous problem to this one, is that now this formulation is an instance of what is called the generalized moment problem. See, you have linear constraint on moments and a criterion to minimize. And so if the data are algebraic of your problem, then you may deploy what you call the moment SOS hierarchy to solve the problem. What do I mean by data are algebraic? Well, the cost to minimize is a polynomial here. Okay? And the support of the measure nu phi, which is S, should be contained in S, sorry. For example, it would be algebraic data if S is a semi-algebraic set, for example, defined by polynomial inequality constraints. Okay? So now we have, from the beginning, we just deploy several steps to now end up with this problem where we want to minimize this cost with lambda, but then you look at the moments of the joint distribution lambda and the moments of the measure nu phi. You can restrict to look at the moment of these two measures. So how do you compute this in practice? So now we are going to, that's basically the steps of the moment SOS hierarchy, that now you introduce, instead of looking at the measure lambda and phi, you look at sequence of what we call pseudo moments, okay? And we say that the pseudo moments of the measure lambda should be equal to mu alpha with respect to x. So this is a moment restricted to x, to the variable x of the lambda, the joint distribution. And when you restrict to y, the second variable, then the moment of lambda, the pseudo moment of lambda should be equal to phi p alpha, which is the alpha moment of the mixing measure phi. And so here I don't go into many details. This is a classical condition because here you see those elements are just vectors of numbers, which ideally should be the moments of the measure lambda and the measure nu phi. Okay, these are scalar vector of scalars, and those conditions. So those conditions are just necessary conditions, semi-definite constraints that are necessary conditions to impose that this vector of scalar lambda and phi are indeed moments of some measure on RD and on S. So these are linear. The entries of those matrices are linear in lambda, linear in phi, and they are just necessary conditions to ensure that the phi you have here is a vector of moments of a measure on S, and lambda is a moment of a measure lambda on R2 on RD times RD. And of course, if you would take into account all n, this would be necessary and sufficient. But since we don't want to have countably many constraints, we restrict to a fixed n, so that's why now we have n here. This will be a lower bound on your tau, the optimal value of your problem, because you restrict to vector of scalar, which are of degree n, and you expect them to be moments up to degree 2n of those two measures lambda and nu phi. But of course, these are only necessary conditions, because we consider only moments up to degree n, 2n actually. Okay, so this is why this is called a relaxation. When we solve this problem, it's a very nice problem because it's a convex problem which can be solved efficiently, but you are not guaranteed when you solve it that the lambda that you get and the phi that you get are moments of a measure are the moment of a measure lambda and phi that you look for. Okay, they satisfy necessary condition, but not all conditions. That's why it's a relaxation. Okay. So now, as I said, lambda is just the moment. So it's a vector of scalar of this dimension. Okay. It's a finite vector up to degree 2n of pseudo moments on a measure on the joint distribution lambda. So we call them pseudo moment because there is nothing in. We have only necessary condition on them to be moments. Similar, same thing for phi. So the lambda and phi that appear in this semi-definite program here, the lambdas and the phi. Okay. So the phi will be a finite vector up to degree 2n of a pseudo moment on Rd times Rs. Okay. So this is because this is the measure, the mass m, the mean m, and the covariance matrix. Okay. Mn of lambda is just the degree n moment matrix of the joint distribution, or pseudo moment matrix, let's say, if you want. And this is called the degree n moment matrix of the pseudo moment sequence J phi. Remember, Dj is just the polynomials that define the set S of the parameter m and sigma. So it's not very necessary to go into details, but just to say that those matrices are linear in the lambda and phi.
So,
yes?
may I ask a question?
Yes, yes.
Is it possible that you have pseudo moments up to all orders, but no final solution? Can that happen? So
you would have all moments, but
I mean, for every degree you cut, right? I mean, you have a solution, but there is no final solution to your problem.
Because of Karleman condition, no, it's well defined. Actually, for every n, there is an optimal solution, and we'll show that it converts. If you take the solution, yeah. Okay. So that's for fixed n as for the question, and because of the Karleman condition. This is the result I was mentioning. So, first of all, because of the Karleman condition, this program here, this semi-definite program, where is it? Yes, this semi-definite program here has an optimal solution for every n, because the set of feasible solutions is compact. Okay. Sorry, I mixed. Yeah. So for every n, there is an optimal solution lambda n phi n of the degree n relaxation, and when n goes to infinity, then the optimal value of this relaxation goes to the distance you want to compute, and any accumulation point of those sequences, because this is a vector of dimension degree 2n vectors, then any accumulation point of these sequences is an optimal solution of the Wasserstein problem. So that's why the solution is not unique in general, okay? But every time you solve a sequence, up to a subsequence, you converge to an optimal solution of your problem.
But if the Karleman condition is not satisfied, this has to fail, right? Or
well, yeah, Karleman here is crucial.
yeah, but if it's not satisfied, you could still have these finite.
Yeah, maybe, yeah, and maybe convergence is lost or
something interesting happens.
Yeah.
Thank
Interesting
you.
or not? Sorry? No, yeah, here because of Karleman condition, you have all moments.
I think, but if you drop that.
Yeah, of course, yeah, sure. Okay. So here, up to subsequences, you get what you want. That the moment of the pseudo moment converts to the real moment of a joint distribution lambda star. That solves the problem. And up to a subsequence, the pseudo moment of the mixing measure converges to the optimal mixing measure, to an optimal mixing measure. Duality, it's interesting because it has a link with a classical dual in optimal transport. So now the optimal transport, the dual of the initial problem, it looks like this. So again, you recognize the classical inequality polynomial q in x and a polynomial h in y, so that this is dominated by the cost, okay? But now instead of you minimize q d mu, but there is no h directly in the cost, but you have a constraint that says that h, so this is the integral of the moment of the mixing the new phi should be greater than theta, and you minimize theta here. Okay. So that's the way the dual looks very much like the classical dual in optimal transport, right? And in fact, you can rephrase this as saying that the dual is exactly equal to this, right? But in fact, you can suppress this term because we can show that the theta can be equal to 0. So in fact, this is the real dual amounts to this. So it has really some flavor of an optimal dual of an optimal transport problem. Okay. So in optimal transport, you would have this term here with the second measure, the second marginal. But here the second marginal is unknown. You have to compute it. So it doesn't appear in the code directly like this. And let me tell you one word about what was our motivation to do that. The application was for unsupervised clustering. Suppose you are given a cloud of points N or D, and let be mu n be the empirical measure, okay? And then if you solve this problem with mu being this empirical measure, you try to see if this cloud of points can be approximated by a mixture of Gaussian. And when you do that, just looking at every step of your relaxation, you look at the moment matrix of your mixing measure. If the rank of this matrix stabilizes, it gives you the number of means. If the rank is finite, it gives you immediately a good approximation of what is the number of clusters. So that was the motivation of this work, and we are just trying to implement this now. So, of course, this was a theoretical result about the existence, the optimal value, and the existence of optimal solution. But then, so we know that the cost converges to what we want, and there is not necessarily unique solutions. Okay. But open question that the uniqueness of the optimal Jones distribution, not necessarily true, but apparently Guillaume Carlier thinks that this should be the case. But on the other hand, the mixing measure, there is no reason why it should be unique. So this is maybe the most difficult part. But if the uniqueness of the Jones distribution holds, then the Gaussian mixture would be unique also. The mixing measure might not be necessarily unique, but the Gaussian mixture would be unique. Okay? Okay. Yeah, as I said, if the rank of this mixing measure, when you solve each relaxation at step n, if you observe that the rank stabilizes to a value r, for example, then you can be pretty confident that the number of clusters would be r, just because there are m possible means. And we can extract those values. Okay. Now I'm going to present basically the same thing, but now with a total variation alternative, instead of going at the W2 Wasserstein distance. So now we look at the same problem, but now so it's exactly as before, but now instead of having the Wasserstein distance here, now we put the total variation distance, okay? And we claim that, assuming that all moments of mu and nu are finite and available, this is, when you solve an optimal transport, total variation problem with a nu here instead of a nu phi, so you want to compute the difference between mu and nu in total variation, the distance between mu and nu. If both of them are finite and available moments, and mu and satisfy Karaman condition, and in case of nu phi, S is compact, then you can compute this. I mean, this is amenable to practical computation, like for the Wasserstein distance. Because total variation is supposed to be a difficult measure of distance between probability measure, but in this case, we can do practical computation efficiently by convex optimization. So to see that why the total distance in total variation distance is difficult, there is if you have two measure mu and nu and you want to compute the total variation distance, which is also W infinity Wasserstein formulation, you see that the cost is very nasty compared to the W2. Okay, it's a cost which is 1 on the diagonal and 0 elsewhere. Okay, and under the same constraints. Or you look at the dual, you have this, or all bounded function with the sup number should be less than 1. And of course, you see that this is quite difficult to solve. The space of f on which you optimize here is too large, okay? And this is well known that this is a difficult quantity to evaluate, okay? And on top of that, even if you would like to approximate, in principle, these constraints immediately tells you that it's not a friendly constraint if you would like to use polynomials, okay? Well, this is not new, okay? But I will try to show you why there is a formulation using the total variation that is nice from convex optimization viewpoint. Ideally, how would you compute the total variation distance between mu and nu of phi? So in fact, you say that mu minus mu phi, which is a sign measure, you write it as a difference of two positive measures, okay, lambda plus, lambda minus. And ideally, when you solve the total variation distance, you want to obtain the Han-Jordan decomposition of the sign measure mu minus phi. This is the whole goal of the total variation. What you want to compute is, in fact, the Han-Jordan decomposition of the sign measure mu minus nu phi. And when you write it like this, then, assuming that this is indeed the total variation, the Han-Jordan decomposition, then the total variation is just the sum of the two masses, okay? This is classical. So if you would like to solve the total variation distance, okay, you introduce those artificial measures of lambda plus, lambda minus. So you want to minimize the sum of the two masses, okay? Under the constraint that the sign measure mu minus nu phi is equal to lambda plus minus lambda minus, and lambda plus lambda minus are just positive measures, and phi belongs to the probability measure on the set S of mixing parameters. So it's very easy to prove that this solution is exactly what you want, but it's just a rephrasing of your problem, okay? By construction, the lambda and Jordan decomposition minimize this problem. It's not very complicated. Okay, so we are going to start from this problem. Now, if mu again satisfies Karl-Lehmann condition, then this solution this problem has an optimal solution. It's an infinite-dimensional LP, okay? But now on moments again. So you replace remember, see, this is a constraint on measure. Say two measures should be the same. And you replace by saying their moments should be the same. Because of Karl-Lehmann condition, you can do that, okay? So you say that those moments should be the same. And lambda plus, lambda minus should be positive now. And again, this is a generalized moment problem, okay? So this has really the optimal solution that you want, but you don't know how to solve it yet. So strategy is, again, you replace the above LPO measure by degree 2n truncated version, semi-definite problem, where the moments of phi and lambda plus, lambda minus up to degree 2n are replaced with pseudo moments up to degree 2n that satisfy degree 2n necessary condition to come from a measure. This is a general scheme behind that. So what you say, now you introduce pseudo moments, so you say you are less ambitious, you are going to compute a lower bound, or n, because you consider pseudo moment up to degree 2n only. So it looks like this, okay? But now you see, instead of considering all moments, you consider all moments up to degree 2n, and again, this has a necessary condition for the pseudo moment to come from a measure. This is a convex problem. But this is not enough, because we don't know if the infimum is attained. And again, there is a nice thing. It's enough to add a very simple constraint that guarantees that you compactify everything. And it comes from an observation on the Han-Jordan decomposition. So suppose that you look at the Han-Jordan decomposition of the sign measure mu minus nu phi. But there is a very simple constraint on the positive part lambda plus and the positive part lambda minus, that it is dominate the positive part. This is the Borel space on which mu is greater than nu phi, okay? And of course, this is less than mu. And on the negative part, where mu is less than nu phi, then the positive measure is less than nu phi. This is a very simple observation on the unjordan decomposition. But then, so this is an information that you have on the optimal solution that you want to look for. You want to compute an optimal solution, and you know that the optimal solution should satisfy this. So you put that in your relaxation, because you know that at the end you have to satisfy this. And the way you add this is that now you say that the moment of the positive part of the unjordan decomposition is dominated by the moment of mu, and the moment of the negative part, lambda minus of the unjordan decomposition, is dominated by the Gaussian mixture. And again, the necessary condition to come from moments. So you still have a convex optimization problem, but it changes everything because now, this convex optimization problem, the feasible set is compact. Just by the crucial additional condition that you have here, guarantee that now you have a nice, well-behaved problem for your pseudo moments. If you get rid of this, the optimal solution is okay, but you don't know how to compute it. Okay? And again, so the result is like that. Suppose the set of mixing parameter is a semi-algebraic set defined by some constraint of this form, like for example, these kind of things. Okay? So for every n, the optimal value is attained as a triplet of pseudo moment. Okay? And now there exists a probability measure of phi star on the mixing, the set of mixing parameter m and sigma, so that when the number of moments goes to infinity, then you converge to phi star, okay? And now you converge not up to a subsequence, but for the whole sequence, okay? Because the unjordan decomposition is unique. So contrary to the Wasserstein distance, now we don't have to go to subsequences. The whole sequence converges because you know in advance that the unjordan decomposition is unique. So the pseudo moment converges to the unjordan decomposition.
In practice, is it easy to figure out what this probability measure is just from looking at the sequence of
of course, but
moments?
You expect that you will see what happens with small n.
Okay.
Of course, the result is only asymptotic.
Yeah.
But you expect that you will see nice things. For example, the mixing, the phi star, this measure phi. Again, you expect that, for example, the number of mean, it will be an atomic measure.
Yeah. Okay.
It's not guaranteed, but you expect that.
And then it's just
Otherwise, it's just asymptotic.
And then it's just some equation to solve to figure out where the atoms are. Okay.
Can I ask one more question? Well, this also looks good, but in the Hahn decomposition, you have to guarantee that the supports are disjoint, right? If not, there could be some exchange. Can you guarantee that in your approximation as well, that the support of the two lambda plus and minus are disjoint?
Well, that, I don't know, because the support could be very nasty. For example, suppose that you could have a measure on the rational and a measure on the reals. So, for example, the support is the same in this case. So
in the approximation, we don't know that the lambda plus n and lambda minus n have disjoint support, right?
Well, we don't know. We have their moments. That's all we have. We still have two distinct.
Oh, you have some information. Yeah.
But describing the support of a measure can be very difficult. Whereas the moments, you could have, for example, think about a fractal measure. A fractal measure could be very nasty. I mean, impossible to describe. But since if your fractal is in a compact set, the moments of the fractal are
good enough.
It still characterize your measure.
Yeah.
You would like to have a picture, but getting the picture is very difficult.
So that's why I was asking, because in the limit you somehow have to guarantee that the limit is objects you obtain with the procedure have disjoint support, right?
Well, you get the limit of the moment to the moment of the unjordan decomposition.
Okay, and that you know.
Yeah, that's what we know. Yeah, that's exactly what you have. The pseudo moment of lambda plus converges to the real moment of the unjordan decomposition.
Oh, you have it because you know the moment. Okay, yeah, sure. You guarantee it indirectly by the moment.
Yeah.
That's true.
And here you don't have any subsequence because it's just the unjordan is unique, so there are no accumulation points. There is only one limit point. And just give you how does it work. Here it's not for the Gaussian mixing of Gaussian measure. I was just did some very simple computation over two measures, mu and nu. Okay, two Gaussian measure, for example, and you want to see how the SDP works to compute the total variation. Okay, there is no mixing, no Gaussian mixture, just to see numerically how it goes. So, for example, you see what happens here. You know that if two measures are disjoint, the total variation is 2. Okay, and you see, for example, if you take a Gaussian, here is univariate, but you take, so you see you have the mean of the first measure mu is 0, the variance is 0, 1, and the second is 1 again, and 0, 1. Okay, so the mean are relatively disjoint. And you see that after going to pseudo moment up toward the 4, you get already almost 2. So it's like those two, you can consider that those two Gaussians, because the mean are very separated and the variance is not very big, it's as if they are disjoint, almost. Whereas if you go to, and the same thing for those cases, but here, for example, no. For example, here, if you take a Gaussian with mean 0 and variance 0.5 and mean 1 with variance 0.5, you see that after 4 degree pseudo moment, you are far from being 2. And so this can be a nice way to sometimes have an idea of how separated are two measures with densities. Okay, of course they overlap somewhere, but the overlap can be very small, and this is reflected in the value. The closest you are to 2 means the closest the two measures are almost disjoint support. And also, what is nice is that when you look at the total variation distance evaluated this way, and you look at the first, and you take the first and second moments. Okay, when you look only at this number here, this column, when you take only moment of order 2, okay, this value is exactly the value. In the case of Gaussian measure, is exactly this value, which is known to be a lower bound on the distance, total variation distance between two univariate measures. So there is an explicit analytical formula that gives you that the total variation distance is greater than 2 times this, and this is exactly the value that you get at the first relaxation.
Is there a multidimensional version of this one?
Sorry?
Is there a multidimensional version of this one?
Is there a what?
Higher dimensions.
No, this formula, I got it in some paper by, I don't even remember the name, but I don't know if it's true for the do you know if it's true? I don't know if it's true in the multivariate case, but okay. So thank you very much for your attention.